Okay.
So the topic I have here is very close to what Professor Dorogovtsev just said. So let me do this. So the main object is a Brownian web, or more specifically the Arratia flow. So this is a collection of coalescing Brownian motions that start from all points of the real line, move independently at its limit, and then coalesce without changing their diffusion. So it's a well-known object. And in 2007, a drift was introduced into this picture in the sense that now every particle moves like a Wiener process, plus some drift. Drift affects every particle independently. This is just indicator that they are equal. So today I will be speaking very briefly about the relation between the Arratia flow and the non-colliding Brownian motions, because that will lead us to some algebraic properties of the Karlin-McGregor determinant. And later we will use those properties to derive some convergence of the densities that correspond to the finite number of starting point to the density and point density that corresponds to the whole flow. I have to say that this is a work in progress. So some things will be formulated without some technical moments, and also we end with a discussion of the current state of the problem. So it is well known that there is a deep connection, and we had last semester a talk by Professor Vovchanskyi exactly devoted to this, between not coalescing or annihilating Brownian motions and random matrices, and the whole algebraic theory behind that. Here I didn't include it full title because these papers are more or less well known here. However, I included the full titles for these three papers because this describes coalescing, non-colliding Brownian motions with fixed drift and gives the explicit expression for the density of such process. This describes algebraic properties, and this paper includes the result that I will be using throughout the talk. So let me quickly recall that if you have a very specific measure on the set of all square matrices, then actually the eigenvalues of the corresponding random matrix values process are non-colliding Brownian motions in Dn, which is just the first simplex, and it's also called the Weyl chamber. And in a moment we'll tell very briefly why it's the Weyl chamber. And this is the SD that describes the drift of non-colliding Brownian motions.
Excuse me, can I ask you about, you consider the unitary ensemble of matrices. It does not depend on T, I think, yes? But then,
yes,
then
you need to include T here.
Where?
Well, I will not be speaking very much about this specific process. I will just need that the fact that it is related in some way to non-colliding Brownian motions, and because it's related in some way, to to obtain the density for non-colliding Brownian motions, for Dyson's Brownian motions, we need to use the Dub's H transform. And the H transform is exactly the van der Monde determinant.
Yes, yes.
Yeah, and this is just the Karlin-McGregor determinant. And then you can see why this we have 1 over this difference, because it is the corresponding logarithm and derivative in a proper sequence. So we see that van der Monde derivative plays an important role here, and we will see that it plays an important role in our situation also. So in the case of coalescing Brownian motions. A very quick explanation why there is this very algebraic expression is that we can consider a so-called root system in Rn, which is a sequence, a finite sequence of vectors such that they span the whole space. After taking minus ek is contained in E, and this relation holds so only ek and minus ek, but not 2/3 ek are contained in E. And the system is closed under reflection with respect to the hyperplanes that are orthogonal to some E, G in the system. And this is, again, describes the ways that you can standardize their lengths. So we have these vectors, they describe some set of reflections and the group of reflections with respect to these hyperplanes. And this is called the Weyl group. And these hyperplanes divide the whole space in the set of disconnected regions. And these regions are called Weyl chambers. So if we have our standard situation where we have non-coalescing or reflecting Brownian motions, we work with the Weyl chamber of this type. And in general, the paper of Grabiner contains examples. You can consider another way, another systems of reflections, and that would lead to another determinants and permanents that describe the density of coalescing and reflecting Brownian motions in those chambers.
So what change of this root set leads to the usual situation for the Dyson diffusions?
Something like that, where epsilon, this is an ordinary basis. Because this is exactly the hyperplane we are interested in.
Okay.
Thank you. So the main object we are interested is endpoint densities or so-called correlation factors. Let me quickly recall the definition. So I have possibly Brownian Arratia flow is drift. So A is drift. We consider all starting point in this set segment from 0 to 1. And sometimes we consider only the finite number of starting points. And then the K point density is a function on Rk is such that this holds. So this is the indicator that we have not less than K points at this time T, and it's just sum of all possible combinations of distinct values. An alternative and more important for us description is this, where Nt is the number of points that got here. Why I'm saying almost? Because you need to add something to their proof to accommodate for the presence of drift. And we will discuss this. But before that, let me recall a result that has been mentioned here for a number of times, that if you define a Pfeffian of a square matrix in this way. We do not need to remember this formula. And we define specific 2 times 2 matrix by using Gaussian kernels. Then it is known that the point process of the Arratia flow is just the Pfaffian point process. That means that this formula holds, which is true actually for any measure with such endpoint densities. This is again NT. And for those who are interested in examples where you can calculate something by hands using this formula, you can visit this paper or Fomichov or Glininet, Fomichov, or some other papers you can find following this links. So let me start with discussing.
Could you please show us previous formula? I can't understand about A1 and AM in the left-hand side. Ah.
So this is like a factorial moment, NT AG to the power
So
K.
you consider product of products, of factorial products?
Yes. So this is a product from G to M of factorial moments.
Okay, thanks.
You're welcome. So now I want to discuss the proof of this formula. So if we have drift, then those densities still exist and are defined with using this formula. So the general idea of the proof is borrowed from the seminal paper. However, you need to add something. And essentially, if you define this measure nu NT of A, which is just the number of points that got into this set, then we have the Gersanov theorem, which I'm not going to repeat because it's a known fact here, that actually says that the law, the Arratia flow with drift, is absolutely continuous in this special Skorokhod space with respect to the law of the Arratia flow with no drift. This result can be extended by carefully examining the proof to the case when drift is just measurable and bounded, and using this estimate, again, from the monograph of Professor Drogovtsev.
Only one remark I have to say that I proved the Gersanov theorem for the space G, not R, but finite interval.
Yeah, yes.
So we have to start from the finite interval and then extend it to all R using usual sigma additivity.
Yeah, this is an important remark, but we are discussing only such starting segments at all. So it's everything is well defined here. Here, if you have also, obviously, if you have unbounded drift, this property fails. And then you combining all these estimates, you can say that you have this existence of densities. And secondly, repeating some recursive procedure in the original paper, we have this estimate. So essentially, we have that our measure, which is used to define our endpoint densities, our correlation function, is absolutely continuous with the Lebesgue measure in Rn. So this gives us the existence, and this gives us an estimate. And using this estimate, we can prove that we can go in this definition from the mathematical expectation of product of the numbers of points to just the indicator, to the product of indicators that those intervals are not empty. So essentially, the probability that we have 2 or more points in some interval of length delta is at least delta n plus 1. because this indicator is less than this product, and this is integral with respect to the square of this, how to say it, segment times the product of all other segments. And this is delta n plus 1. So this is an important calculation that we will be using a couple of times later. Now, if you have a finite number of coalescing process, you can define a so-called coalescence scheme. This just allows you to describe the order in which collisions happen. So you just, we don't need the specific way it is defined. We just need to know that for every way collisions happen, we can define a unique coalescence scheme. Every coalescence scheme defines the only sequence of the unique sequence of collisions. So you just enumerate them from up to bottom, and if collision happens, you write down the number of the lowest particle in this pair. Then you enumerate them anew and repeat the procedure. And then by, again, this is you can define an n-point density, a k-point density that corresponds to n starting points. So you here have the same definition, but now you consider not all a flow, but just a finite number, and the rest of the definition is the same. And you can define also the endpoint density that corresponds not only to the finite number of starting points, but also to the specific way coalescence happens. So S of X, this is the coalescence scheme for this configuration. XA, UN. And the rest is the same. They are well defined, again, because of the Girsanov theorem for the Arratia flow. And if we have no drift, we can consider a sequence of partitions on the interval, for instance, 0, 1, that satisfies this equation, and such that delta n, which is the maximum difference between 2 points of the partition, goes to 0. Then this convergent holds, but also you can prove, you can check the speed of convergence of the corresponding one-dimensional density when you start from all points from this specific partition to the density when you start from the whole segment from 0 to 1. And this is delta m squared. By hands, you can actually check that this is also true for two-dimensional density, as the speed is the same. And we will see, we will prove that the speed is the same for all densities. So let me recall the main idea of this relation, that essentially we are talking about heating x1 plus epsilon, x2 plus epsilon. So we know that there is some point of the original Arratia flow that hits this interval. Now, for every Arratia flow, there exists a dual Arratia flow in the reverse time, such that the trajectories of these two flows do not intersect. So this means that the Arratia flow in the reverse time moves as follows. So they do not meet the Arratia flow, the particles in the dual Arratia flow, which in the case of the Arratia flow with zero degrees, it's just the original Arratia flow in distribution, starting from xk plus epsilon, do not meet. So we can reformulate the problem of heating some non-intersecting segments in the problem of Brownian motions that start from the ends of these segments not meeting at all. However, this may happen, obviously. And if you have here some discrete set of starting points, then you can relate the situation where the original flow hits this interval, but particles that start from this specific set do not hit, in the way that this means that the Arratia flow in the reverse time should hit between two subsequent points, and this is delta m. When you are doing this and you want to do a general case, general n-dimensional case, you need to think about this Karlin-McGregor determinant. And you can see that if you start from, you have n intervals, so you have n-dimensional points, you need 2n particles in the dual flow. And we are interested when this happens. So exactly when this goes to 0, this goes to 0 in pairs. And for a long time, I didn't know how to do that. I even thought that you need to try decomposing this sum into some subjugated classes, but it doesn't work because there is a trivial class that consists of a trivial permutation. However, later I find a proper way to do is by decomposing the Karlin-McGregor determinant in terms of symmetrical polynomials. And I would be speaking what follows about probabilistic half algebraic and PDE-based proof, such convergence results. This is work in progress, so there might be some things. So we have a number of definitions of Karlin-McGregor determinant, the standard one. This decomposition in terms of the Haar measure on this UN group of matrices, and this decomposition. So this is like a radial part, and this is Q-symmetrical part.
UN is a group of unitary matrix.
Yes.
Yes.
Mm-hmm. And using this second relation in this paper, the author obtained a number of results, but I will be citing only two of them. The first one gives a very powerful, simple, precise and concise estimate for the Karlin-McGregor determinant in terms of Gaussian densities. This is just one-dimensional Gaussian density. And we have also this simple and nice estimate. So this is very nice estimate. And
so it says that it is enough to consider exactly two permutations. One is trivial and another one is backward.
Yes, this is exactly, because here they will need to this is exactly what the Hovding inequality for maximal and minimum correlations.
Mm-hmm.
The same idea.
Mm-hmm. Mm-hmm.
And the only problem with this estimate, which I was going to call the first estimate, is that it doesn't provide that much information about the derivative of the Karlin-McGregor determinant. And sometimes it is needed. However, there is the second result that I was able to discover. only recently, though the paper has been laying on my laptop for years. Or maybe I just managed to appreciate it. There is a result, Katori and Tanemura, that gives another decomposition of the Karlin-McGregor. So again, we have so this is skew-symmetrical function. So this is skew part, and this is symmetrical part. I will explain in a moment what are these polynomials and how to define them in two different ways. So let me start with describing what the sum is. So this is an infinite sum, and over all partition set of non-integers. So starting from some place, there are just zeros, and this is we say that this is a partition of this integer, and then we can define the so-called Schur polynomial over the only problem here is that should be m here and n here, as this n and this m are not related. And then you define this polynomial. So this is determinant divided by the van der Monde determinant. And this is called the number of positive elements in the partition. So this is just essentially a number of blocks you split your integer in. As such, polynomials form a basis in a proper sense that there exists a function that can be understood as the inner product and so on. And here you have essentially the decomposition in terms of symmetrical polynomials. Now, an alternative, and for me it was a more clear definition of the Schur polynomial is as follows. So again, if you have some partition with k non-zero elements, it defines a Young diagram in the sense that you just take mu1 empty boxes, then mu2 empty boxes, mu3 empty boxes, and so on. So for instance, 3, 3, 3, 2, 2, 1 describes a partition of 9. This is a diagram. Now you define a so-called semi-standard Young tableau, and you fill these boxes with all numbers from 1 to n, where n again is not related to this k, in such a way that numbers are not decreasing across each row. So you can have 1, 1, 1, 1, 2, 2, and numbers you can have 2, 2, 2, and numbers are strictly increasing across each column. So this is a nice way to enumerate all possible polynomials in x1, xn variables. So this is called the shape, and you take the set of all semi-standard Young tableaus of this particular shape mu. Here is mu, and you calculate how many times number 1 appears in this particular filling, and then you consider this product. And by definition, you have also 1 here. So returning to this expression, there is 1 plus infinite sum here. Now, using this result, we are able to discuss this theorem. So suppose that this is just guarantees that essentially it can be replaced for simplicity with the assumption that our partition are duadic. This is just guarantees that we do not have very small elements of our partition, very large elements of our partition. And then for any n, zero drift is zero. The speed of convergence of this n point density that corresponds to the number, well, here should be some, not m, but some nm. So nm is the number of points in UM. So it always has the speed, and the coefficient can be calculated directly. So this is the sum of limits of this expression. So we have here that exact, if you consider, here we should consider like the dual Arratia law. We do not have meetings for those that are close, that start close to each other. And we see that exactly one pair misses the point of the partition UM. All others actually hit, in the sense that only X, those starting UK plus epsilon miss, it gets in between the points of partition, but all others actually get this situation. And there is no coalescence happening in this situation. You can rewrite in terms of Karlin-McGregor determinant, but I don't think it adds anything.
Excuse me, can you just go back to the previous, to this one? Okay. How do you know that this limits exist in the last line, limit and epsilon tends to 0, epsilon and minus n power?
We will see why it exists, I hope.
Mm-hmm. Because because this decomposition, looks like we can do it just using dual flow.
Yes.
Yeah, exactly. Yeah.
Yeah.
So I just want to understand where is the main problem. Here we just have to prove that these limits are positive. Maybe, yes?
Yes.
Okay. Okay.
But, and the reason why it's positive, because if you do not have coalescence, you can rewrite it in terms of the Karlin-McGregor determinant, and for it we have the first estimate. Let me find it.
So we have estimate for two sides, yeah?
Yeah. Let me find it. Where it is? Here. It's here.
So it solves the problem in a sense that when we consider derivatives of our Karlin-McGregor,
they do not appear here.
We can say that they are positive, yeah?
In the sense, yes, but on the boundary.
Yes,
exactly.
Yes.
Yeah. And they do not even appear here because we do not have meetings. We will see that if they appear, you need to use the second estimate to get rid of those terms.
Okay.
So essentially, we need to estimate this expression. So by the Lebesgue differentiation theorem. So the claim one, that we can get rid of, so this is like the product, mathematical expectation, the product of numbers. And the first step is that you can get rid of those products and replace them with just the indicators that there is at least one particle. So NT is the original from 0 to 1, and N is for this, the finite number of points. And again, we just discussed that this is true because we have a good way to speak in terms a good way to estimate such expression. So this is of order epsilon plus 1. So it disappears in the limit.
This is due to that we have n
Estimates
point
probability.
densities. Mhm, mhm.
So it's either because we use those estimates from the proof of the existence,
Yes, yes,
or
exactly. Mhm,
yeah,
okay.
or we can use the first estimate.
Mhm, okay.
And here it also works. So now we just get what we need. So essentially, here is this x1 plus epsilon, x2 plus epsilon. So we know that this is dual flow. These do not meet. And I want to impose exactly the conditions that only if this is like the points of our partition UM, then exactly one pair gets in between the points, and all other pairs actually have something like this. Or they hit the same this is some UMJ, UMJ plus 1. And I also want to get rid of the possibility that we have coalescence between these pairs, because it's not forbidden by this relation. Sorry. And for that I will need the following result. If you have Lipschitz or at least Holder continuous and bounded function, we can consider the standard initial boundary value problem for the Laplace the parabolic problem. And if you define this part of the boundary and define the surface measure of the boundary and define the outward normal derivative, and even if you have some drift, so this is the fundamental solution. If you add here minus axk dxk, I'm sorry, I forget to write this here. And then you can solve this equation in the sense that if you have a specific coalescence scheme, that the J point density that corresponds to the Arratia flow with drift A, the set of points X, which belongs to Rn, and a specific coalescence scheme is described as an iterated double layer potentials, etc. So you live until first collision happens, you live until second collision happens, and you know exactly which part of the boundary you get into because you fix a coalescence scheme. And in the end, you have all those particles that have survived, and we just like consider J of them because they maybe K, there are K particles that have survived, and you need only J of them. So this is a result from my thesis. It slightly generalizes the result from the paper of Drogovtsov and Vovchanskyi. So essentially, I want to get rid of these four terms. Here is the term that two pairs get into the same segment of the partition, and there is no coalescence. Here, the same situation, but there is coalescence. Here, two pairs simultaneously get into two different segments of the partition, and there is no coalescence, and two pairs gets into different segments of the partition, but there is coalescence. If there is no coalescent, we can use the first estimate. Here we will need to use the second estimate. And this is exactly because we have here derivatives, why we need something that is slightly more strong. So now I consider only admissible coalescent schemes, because we know that coalescent schemes of 2j plus and 2j does plus 2 does not meet. This is forbidden for the first by this. So only such collisions are possible. And I will consider only one term, this P4, and then I can say that this relation holds. So we estimate we sum of all possible coalescent schemes that satisfy this condition. And then we need to integrate this two-dimensional, two-point density. And x epsilon, x1 plus epsilon, x2 plus epsilon, and so on. So if we fix now coalescent scheme, we have this expression. Now, y1 and y2 belongs to the interval of size lengths delta m. And if you look at this expression, here we have something like this. So we have this van der Monde determinant. This allows us to conclude that this is already less than m to some positive density, to some positive degree. And also because we have here x epsilon, and we differentiate only with respect to that one, that means that this term, if you put here epsilon, is left unchanged, we can get also epsilon n. And this is important because we want limit over delta and limit over epsilon. And then we have another delta m squared here. And that allows us to conclude that this term disappears in the limit, in the second, after taking the second limit. And something like this can be done with all those terms. And that's, in the end, we will end with this result. It is possible to get it by hands for two-dimensional without knowledge of these important estimates. Now, I want to talk about some work in progress. There are still here somewhere some technical details, but in general, I think it's more or less true. However, now I want to speak about the following idea. So we obtained this convergence for this case where there is no drift. We obtained it because in this expression, in particular, we know how this behaves.
Mm-hmm.
But when drift is non-trivial, we do not know actually how this behaves. So my idea was initial, okay, but we know how to represent endpoint density in the presence of drift as some perturbations of the densities in the case where there is no drift. And then we can return to the original problem, and maybe we can prove the convergence result for also Arratia flow with drift. So let me recall the result from this papers. Pirgovtsev and Vovchanskyi. This is arXiv, and it also to appear in stochastics. So we consider just unique weak solution of this. Drift is just bounded and measurable. And we define the time when these two processes, diffusion process, meet. And then if we consider a distributional solution of this equation, y minus because we need to go to the dual flow, and this is such operator, so drift affects every particle separately. We start with 1, we do not hit the boundary, and so this is the probability that we do not hit the boundary at all up to moment s. And then we know that proved that this holds. So this derivative, this or minus this. And we did in particular by constructing the solution as such series. So the sum of such iterated integrals with these specific kernels. And in case so this, and what corresponds to the n equal to 0 is exactly the case of the Arratia flow with no drift. And it was easy to establish because after integrating with respect to all special variables, we are left with such estimates, and there is a nice way to estimate them in terms of gamma functions. So it allows us to say that terms of the original series and the derivatives are well defined, and the corresponding series are convergent uniformly. So the whole series is also differentiable, so on. Now, we are aiming, I am aiming to discuss the following. Suppose that we have now x, and we want to obtain this formula. This is essentially the probability that particles starting from xk and xk plus 1 do not meet. And if there is no drift, this is a well-known relation. You can find that in the corresponding paper where the first estimate was given. So again, now I consider two-dimensional situation, parts of the two-dimensional boundary, and recall that this is the derivative with respect to the outward normal along. So each admissible coalescence scheme defines some boundary conditions, where they can hit or where they cannot hit. So this is the sum of indicators of some hyperplanes. So there's the suspect that we fixed some coalescence scheme, and this defines some boundary condition. The starting condition is the same. And formally, if you just write the solution in terms of the green function, you obtain this. This is boundary. This is left-hand side, the source part. And if you try to iterate this, you arrive with this representation. So this is the probability that we are still inside of the D2n at moment t. This is the double layer potential standard. This is a term that is exactly the same, more or less is the same that in two-dimensional case that we have considered previously. And this is what appears because we can have coalescence. But recall that in case of zero drift, this term disappears because we stated that in the finite expressions, there is no possibility for coalescence to happen. Now, as of now, you see there is second derivative here, essentially. This is somewhat problematic. But I suspect that something can be done here, because if A is a Schliz holder, then we have a classical solution, and the solution also in Sobolev space. And if A is just like L-bound, and if you forget that we have unbounded region and suspect that we have a parabolic problem with a very good second order terms, and at least L2 is this boundary drift, then the solution is in Sobolev space. And moreover, their Sobolev norm is controlled by the norm of the boundary and initial values in L2. So I think that there might be a possibility by using those estimates in Sobolev space, or by using the direct expression for the Karlin-McGregor determinants that we now have, to estimate this uniformly. Because if you try to do this in an A way, obviously it gives you something like from 0 to ds1, ds0, s0 to the power 3, 2. And obviously this is not well defined. So right now I'm occupied with finishing the previous part and trying to make sense of this, or trying to get rid of this part. In the sense that we have another representation of n-dimensional density, actually in terms of some exponentials of Brownian bridges. So maybe it is possible to prove that we do not need this coalescence, because we have this some estimates of these exponentials. As a development, I can see that we can think about introducing linear drift, because in real life models that you can find, they love unbounded drift, and even only local ellipses in general, so like cubic. But this requires going back and essentially redoing some stuff, because you need to check that the Gusanov theorem is drift is linear, is of at most linear growth, I think still holds, but you need to be careful of all other statements, especially since you do not have those nice estimates of the probability. Do not meet as CTU minus V, it disappears, obviously. Now, it would be nice about examples. There is this interesting conclusion in all of this, that if you return to this result here for one-dimensional density, you can see that when times goes to 0, the way drift affects the motion of the particles actually disappears. And obviously you can decompose them in terms of powers of t. So this was somewhat unexpected for me, that even though drift affects how they move, for small t it doesn't matter at all. So obviously if you want like drifts that create some high density places, you need t to be positive. And that is a question I don't know how to deal right now with. And essentially that's all I wanted to tell today.
Okay, thank you very much. And maybe somebody have comments or questions, please. Okay, it seems that when we have drift and have the same coalescing scheme as before for Brownian case, then we get the problem with the densities of non-Killet processes.
Yes.
Yes. It is reasonable that we have not now good algebraic representation, but still we can try to get estimation and to get this representation with symmetric and antisymmetric part. It will be functions, not polynomials, but still I think you can think about such calculations. And then maybe one can check that it will have good properties.
So yes, I need to develop a good way to replace those explicit representation in terms of simpler functions.
Exactly, yes. And it seems reasonable that it can be done.
No, yes, I think, but I need to think about it.
Also about your remark that shift does not have any efficient perturbation in the when t tends to 0. It's reasonable because linear trajectories are more fluctuable around 0 than any differential function. So, yeah. So this is the reason why it happens. Okay, thank you again for interesting talk, and I hope that it will end it with a good result about the same behavior when we have a drift.
Yeah, I also hope. At
Okay.
least I will try.
Okay, thank you again, and
You're welcome.
I think that next speaker will be Olga Arasova. Am I right? Georgi. Georgi maybe is absent, but as far as I remember schedule, next speaker is Olga Arasova. So thanks everybody and see you next week. Bye.
Bye bye.